Hey, welcome to this video, and in here I'm going to introduce a pretty important topic in statistics, which is called test of significance. And you're going to carry something called inference toolbox throughout this journey. And what does that mean is that it contains 4 steps for a significance test, also called a hypothesis test. And you will see the meanings of these terminologies pretty quick as I'm going through this. So don't panic if you kind of lost in here right now. So the first step is that the state, population, and parameter state hypotheses. The second step is name your procedure with significance level and check conditions necessary to run test. Third is run test to obtain the test statistic. Fourth is interpret the test statistic in context. And if you want to shorten those, this will be in 4 terms: state, plan, do, and conclude, as we did in previous videos, which we did an example for the confidence interval. But let's focus on the main things in here. So use this example as something that we're go through it right now. Is that last year the mean amount of money spent on music by all U.S. teens was $75. Standard deviation is $25. We hypothesize that the mean for all CCH students is more than $75. We take an SRS of n is equal to 60 CCHS students and get X bar, which is $82. So there's a pretty lot of information in here. So what we want to do is that we want to follow these 4 steps as we go through this test. So first, hypotheses. It basically breaks down into two types of hypotheses, and the first type is null hypotheses, which we use this notation right here. And in this case, we haven't put any numbers in here. Just in general, I want you to know some definitions down here. The mu is going to be equal to some number. And another type is the alternative hypotheses, which we use H sub A as the notation for this. And in here, it breaks down to a lot of situations. It can be greater than a number, it can be less than a number, it can be different with a number. Well, the first two, like either greater than or less than, is going to be one-tailed test. And the last one, which is not equal to, is going to be two-tailed test. You will know what I mean by those as we walk more examples right here. So the second part is significance level. What is significance level? We use this little notations right here, which is alpha. And alpha, it can be equal to any numbers given to us, or sometimes we have to make up for our own. But usually it's those type of numbers, and those are the cutoffs of our whole data. And the third part is we're going to run test. And as we run test, always have to draw the normal curve right here. And as we label our mu, it's going to be the null hypothesis right here. And we use the X bar. This is the sample mean that's given to us, or sometimes we have to calculate on our own. Depends on the situation, but either or we calculate it and we draw it right here. And we will know if it's less than or equal to from our alternate hypothesis. So you can see that alternate hypothesis and null hypothesis work very well to each other. They are pretty close enough that we cannot separate them as when we are doing our analysis or calculation for this test. So any of those, basically those area, it's the probability or p-value in here. And p-value is also a pretty important thing that we have to state in our conclusion and our calculation as we do the test. Okay, fourth part is conclusion. Conclusion is that basically we have to use the statement either p-value less than alpha or p-value is greater than alpha. Only these two situations. When it's less than alpha, we reject the null hypothesis. When it's greater than alpha, we fail to reject hypotheses. You might be thinking why we just don't say we agree with null hypothesis. Well, we can never say something that's directly opposite with reject because we don't have that enough evidence or enough confidence to say that. The only thing we can say is that we don't have enough evidence to reject null hypotheses. So be aware of the wording. Okay, so let's work on the examples that we just see in here. So just restate all of the informations. First, the state part is that mu is equal to average amount of money spent on music by CCHS teens. And our null hypothesis is going to be 75 in here, right here. And our alternate hypothesis is going to be mu greater than $75, I'm sorry, because we think we hypothesize that is more than $75. That's it. The second part is going to be z-test. So what is the name of our procedure or our test? Well, this is a z-test for one mean. And we're given us the alpha is 0.05, which in this case, it does not specifically state in our example, but we just use 0.05 as the alpha value in this case. And there are 3 conditions we have to make sure that we satisfy all. First is the SRS of CCH students. And is that true? Well, it is because it states in the question. And the second condition is that is it more than 600 CCH students? Well, it is because basically this second condition is testing us, is it the sample size less than 10% of the whole population? Well, it is because this high school has more than 600 students. So it's true, so then we can draw the conclusion, which is the standard deviation of the sample is going to be equal to standard deviation of the population divided by the square root of sample size, which is this in here, 25 divided by square root of 60. And the third condition is going to be n is equal to 60 because this is the sample size right here given to us. And is it greater than 25 or not? Well, it is. So we can draw the conclusion that sampling distribution is approximately normal. Some textbooks will use like 30 as the cutoff point. Whatever you're using, like just follow your guidelines made by your professors or textbook or teachers. But I think 25 in my case is enough, so I will use that, stick with it. Okay, so let's move on to the third part, which is drawing the diagram. And it's also like you have to make sure that you really draw a normal curve right here. So make sure there's no like significant skew left or skew right. So we're using our mu, which is 75 in here. This is also the null hypothesis for our normal curve. And what we're given to us, the X bar is $82. Oh, sorry. Okay, so we label it right here. So because we want to test the, like our alternate hypothesis, mu greater than 75. So this determines like which region should we shade it. Are we going to shade it above or below? Well, because we hypothesized it's above. Well, which means that we have to shade it above, which is above 82. Okay, so after we draw this, we will have to do the test statistics, and one of them is going to be the z-score. Remember, z-score formula is going to be x minus mu divided by the standard deviation. In here is going to be 82 minus 75 divided by 25 divided, I mean like just the whole thing, like whole stuff right here. And this is the thing we calculated before above here, and we get this 2.17 as our z-score. And then the second part is that we're going to calculate the p-value. We're actually going to do it on the calculator, pretty easy. What you're going to do is that you're going to basically finding the area of this shaded region right here. So then after you find the area, that's what the p-value stands for, which in this case is a pretty small number. So after we do all of those, we're going to draw our conclusion, which is our last but not least step in here. It's pretty hard for me to adjust the size of the window. Okay, I think that's okay. Okay, so since p is equal to 0.0150, which is less than alpha, remember we're using the 0.05. This is less than alpha, so we reject HO, or null hypothesis, meaning we have enough evidence to say that CCHS teens spend on average more than $75 on music. Remember to state the on average on your conclusion all the time. This is a keyword that you cannot forget. And yeah, and then because it's less than, so remember what we did on the notes before. If it's less than, then we reject the null hypothesis. If it's greater than, we will fail to reject the hypothesis. We never say it's agree or something else, then fail to reject. Okay, so let's move on to another example in here. I want to do this with you guys because this is a very interesting one and I think it's going to be important. Okay, elsewhere in our factory, we have a soda machine that fills soda bottle according to a normal distribution with a mu is equal to 12.1 ounces of soda and a standard deviation is equal to 0.05 ounces. We think this machine may be miscalibrated, but we are not sure if it is producing too much or too little soda on average. We take an SRS of n is equal to 5 sodas and obtain a sample mean amount of soda, x bar equal to 12.14 ounces at the alpha equal to 0.05 level. Do we have enough evidence to conclude that the machine is miscalibrated? Okay, pretty long question, but basically we're doing the same thing as we did before. Firstly, we're going to state that mu in this case is going to be the average amount of soda produced by this machine, and the HO, which is null hypothesis, is going to be mu is equal to 12.1, and the alternative hypothesis, well, this one is not equal to 12.1. It's not either like greater than or equal to, no, like greater than or less than, because in the question it does not say we hypothesize that it's going to be greater than or less than. Like it's only say that we are not sure if it is producing too much or too little, meaning that we don't know it either. Like we don't know how, like what amount will the soda been produced, like compared to the null hypothesis mu, like 12.1 ounces. So which means that we just know that it's going to be different, but we not really sure it's going to be above or below. So make sure the difference in here. And the second part is going to be plan. And first of all, the name of the procedure is going to be z-test for one mean, and state the alpha. In this case, is given to us. Use the alpha at 0.05 level, which we do it right here. And check the conditions. First, is it SRS? Well, it is because it's stated right here. And is it like more than 50 bottles produced? Because we use the sample size of 5, we want to make sure that our sample size is less than 10% of the population. And in this case, it's going to be true, which we can draw the conclusion that standard deviation of the sample is going to be equal to the standard deviation of the population divided by the square root of sample size. In here is going to be this number. And the third condition is going to be production population. Is it normal? Well, the question given to us a normal distribution. So if the question already stated to us, then we can safely say that the sampling distribution is approximately normal. Well, I mean, like I will add approximately normal just to be more precise in here, but because the question already given to us is normal distribution, I mean, it depends on you, but I will state it right here. Okay, the third part is going to be do, which is mechanics and calculate interval, and draw the normal curve right here. Use the mu, which is also the null hypothesis, as the mu of the normal curve. Also use the x bar 12.14. So 12.14 is going to be the right side of the mu, but like kind of see the range, like the difference from 12.14 to 12.1, which is going to be 0.13, right? So those range, because we do not know if it's less than or equal to, we have to do another value on the normal curve right here, which you're going to be use 12.1 minus 0.13, and you will get 12.06 right here. So shaded the region like either less than or more than, because we don't know, so we want to make sure that we consider all the situations. Which means that our z-score will be same thing, x minus mu and divided by standard deviation, and this will give us the 1.79 for our z-score in here, and that's the z-score in here. I'm just checking if that's correct or not. Seems correct. And the p-value in here, because we want to make sure that all of those tails we consider. This is a two-tail test. Like all of the questions that we did above, like if you want to take a reference in here, we did the one-tail test, but in here the biggest difference is that this is a two-tail test, which means when we do our p-values, we don't we're not only doing the area of those of this part, but we also want to consider the area of this part. But because that those areas have to be equal to each other, then we can simply multiply this number by 2. This number is the area of those parts, so multiply this by 2, or you can calculate this area first and then multiply by 2, depends on you, but we can get a p-value of this. So the last part is draw our conclusion. Since p is equal to 0.0736, it's going to be greater than alpha, which is equal to 0.05. In this case, we failed to reject a null hypothesis, meaning we do not have enough evidence to say the machine is miscalibrated. Or you can say that to say the average amount produced is different from 12.0 ounce. But make sure that either of these conclusions state the average. This is a keyword in here. Okay,